Code division multiple access is a channel access method used by various radio communication technologies. CDMA is an example of multiple access, which is where several transmitters can send information simultaneously over a single communication channel. This allows several users to share a band of frequencies. To permit this to be achieved without undue interference between the users, CDMA employs spread spectrum technology and a special coding scheme. CDMA is used as the access method in many mobile phone standards such as CDMA1, CDMA 2000, and WCDMA, which are often referred to as simply CDMA. History: the technology of code division multiple access channels has long been known. In the USSR, the first work devoted to this subject was published in 1935 by Professor Dmitry Vyagov. It was shown that through the use of linear methods, there are three types of signal separation: frequency, time and compensatory. The technology of CDMA was used in 1957, when the young military radio engineer Leonid Kupriyanovich in Moscow made an experimental model of a wearable automatic mobile phone, called LK1 by him, with a base station. LK1 has a weight of 3 kg, 20 euro 30 km operating distance, and 20 euro 30 hours of battery life. The base station, as described by the author, could serve several customers. In 1958, Kupriyanovich made the new experimental pocket model of mobile phone. This phone weighed 0.5 kg. To serve more customers, Kupriyanovich proposed the device, named by him as Correlator. In 1958, the USSR also started the development of the Altai National Civil Mobile Phone Service for cars, based on the Soviet MRT 1327 standard. The phone system weighed 11 kg. It was placed in the trunk of the vehicles of high-ranking officials and used a standard handset in the passenger compartment. The main developers of the Altai system were VNIIS and GSPI. In 1963 the service started in Moscow, and in 1970 Altai service was used in 30 USSR cities. Uses: one of the early applications for code division multiplexing is in the global positioning system. This predates and is distinct from its use in mobile phones. The Qualcomm standard is 95, marketed as CDMA1. The Qualcomm standard is 2000, known as CDMA 2000, is used by several mobile phone companies, including the Globalstar satellite phone network. The UMTS 3G mobile phone standard, which uses WCDMA. CDMA has been used in the Omnitrax satellite system for transportation logistics. Steps in CDMA modulation: CDMA is a spread spectrum multiple access technique. A spread spectrum technique spreads the bandwidth of the data uniformly for the same transmitted power. A spreading code is a pseudo-random code that has a narrow ambiguity function, unlike other narrow pulse codes. In CDMA, a locally generated code runs at a much higher rate than the data to be transmitted. Data for transmission is combined via bitewise XOR with a faster code. The figure shows how a spread spectrum signal is generated. The data signal with pulse duration of a 0-1 registered trademark ED with a code signal with pulse duration of. Therefore, the bandwidth of the data signal is and the bandwidth of the spread spectrum signal is. Since is much smaller than, the bandwidth of the spread spectrum signal is much larger than the bandwidth of the original signal. The ratio is called the spreading factor or processing gain and determines to a certain extent the upper limit of the total number of users supported simultaneously by a base station. Each user in a CDMA system uses a different code to modulate their signal. Choosing the codes used to modulate the signal is very important in the performance of CDMA systems. The best performance will occur when there is good separation between the signal of a desired user and the signals of other users. The separation of the signals is made by correlating the received signal with the locally generated code of the desired user. If the signal matches the desired user's code, then the correlation function will be high and the system can extract that signal. If the desired user's code has nothing in common with the signal, the correlation should be as close to zero as possible. This is referred to as cross-correlation. If the code is correlated with the signal at any time offset other than 0, the correlation should be as close to 0 as possible. This is referred to as autocorrelation and is used to reject multipath interference. An analogy to the problem of multiple access is a room in which people wish to talk to each other simultaneously. To avoid confusion, people could take turns speaking, speak at different pitches, or speak in different languages. CDMA is analogous to the last example where people speaking the same language can understand each other, but other languages are perceived as noise and rejected. Similarly, in radio CDMA, each group of users is given a shared code. Many codes occupy the same channel, but only users associated with a particular code can communicate. In general, CDMA belongs to two basic categories, synchronous and asynchronous. Code division multiplexing, the digital modulation method is analogous to those used in simple radio transceivers. In the analog case, a low-frequency data signal is time multiplied with a high-frequency pure sine wave carrier, and transmitted. This is effectively a frequency convolution of the two signals, resulting in a carrier with narrow side bands. In the digital case, the sinusoidal carrier is replaced by Walsh functions. These are binary square waves that form a complete orthonormal set. The data signal is also binary and the time multiplication is achieved with a simple XOR function. This is usually a Gilbert cell mixer in the circuitry. Synchronous Cdma exploits mathematical properties of orthogonality between vectors representing the data strings. For example, binary string 1011 is represented by the vector. Vectors can be multiplied by taking their dot product, by summing the products of their respective components and V equals, then their dot product where V equals AC plus BD. If the dot product is 0, the two vectors are said to be orthogonal to each other. Some properties of the dot product aid understanding of how WCDMA works. If vectors A and B are orthogonal, then AND. Each user in synchronous CDMA uses a code orthogonal to the other's codes to modulate their signal. An example of four mutually orthogonal digital signals is shown in the figure. Orthogonal codes have a cross-correlation equal to 0. In other words, they do not interfere with each other. In the case of AS 95 64-bit Walsh codes are used to encode the signal to separate different users. Since each of the 64 Walsh codes are orthogonal to one another, the signals are channelized into 64 orthogonal signals. The following example demonstrates how each user's signal can be encoded and decoded. Example. Start with a set of vectors that are mutually orthogonal. An example of orthogonal functions is shown in the picture on the right. These vectors will be assigned to individual users and are called a code, chipcode, or chipping code. In the interest of brevity, the rest of this example uses codes, V, with only 2 bits. Each user is associated with a different code, say V. A 1-bit is represented by transmitting a positive code, V, and a 0-bit is represented by a negative code, a EuroV. For example, if V equals and the data that the user wishes to transmit is, then the transmitted symbols would be V, a EuroV, V, equals. For the purposes of this article, we call this constructed vector the transmitted vector. Each sender has a different, unique vector V chosen from that set, but the construction method of the transmitted vector is identical. Now, due to physical properties of interference, if two signals at a point are in phase, they add to give twice the amplitude of each signal, but if they are out of phase, they subtract and give a signal that is the difference of the amplitudes. Digitally, this behavior can be modeled by the addition of the transmission vectors, component by component. If sender O has code and data, and sender 1 has code and data, and both senders transmit simultaneously, then this table describes the coding steps. Because signal O and signal 1 are transmitted at the same time into the air, they add to produce the raw signal, 1, a Euro 1, a Euro 1, 1, 1, a Euro 1, 1, a Euro 1, plus equals. This raw signal is called an interference pattern. The receiver then extracts an intelligible signal for any known sender by combining the sender's code with the interference pattern. the receiver combines it with the codes of the senders. The following table explains how this works and showed that the signals do not interfere with one another. Further, after decoding, all values greater than 0 are interpreted as 1 while all values less than 0 are interpreted as 0. For example, after decoding, data is, but the receiver interprets this as values of exactly 0 means that the sender did not transmit any data, as in the following example, assumes signal O equals as transmitted alone. The following table shows the decode at the receiver. When the receiver attempts to decode the signal using sender 1's code, the data is all zeros, therefore the cross-correlation is equal to 0 and it is clear that sender 1 did not transmit any data. Asynchronous Cdma. When mobile-to-base links cannot be precisely coordinated, particularly due to the mobility of the handsets, a different approach is required. Since it is not mathematically possible to create signature sequences that are both orthogonal for arbitrarily random starting points and which make full use of the code space, unique pseudo-random, or pseudo-noise sequences are used in asynchronous Cdma systems. A PN code is a binary sequence that appears random but can be reproduced in a deterministic manner by intended receivers. These PN codes are used to encode and decode a user's signal in asynchronous Cdma in the same manner as the orthogonal codes in synchronous Cdma. These PN sequences are statistically uncorrelated, and the sum of a large number of PN sequences results in multiple access interference that is approximated by a Gaussian noise process. Gold codes are an example of a PN suitable for this purpose, as there is low correlation between the codes. If all of the users are received with the same power level, then the variance of the MAI increases in direct proportion to the number of users. In other words, unlike synchronous Cdma, the signals of other users will appear as noise to the signal of interest and interfere slightly with the desired signal in proportion to number of users. All forms of Cdma use spread spectrum process gain to allow receivers to partially discriminate against unwanted signals. Signals encoded with a specified PN sequence are received, while signals with different codes appear as wideband noise reduced by the process gain. Since each user generates MAI, controlling the signal strength is an important issue with Cdma transmitters. A CDM, TDMA, or FDMA receiver can in theory completely reject arbitrarily strong signals using different codes, time slots or frequency channels due to the orthogonality of these systems. This is not true for asynchronous Cdma. Rejection of unwanted signals is only partial. If any or all of the unwanted signals are much stronger than the desired signal, they will overwhelm it. This leads to a general requirement in any asynchronous Cdma system to approximately match the various signal power levels as seen at the receiver. In Cdma cellular, the base station uses a fast closed-loop power control scheme to tightly control each mobile's transmit power. Advantages of asynchronous Cdma over other techniques: efficient practical utilization of the fixed frequency spectrum. In theory, Cdma, TDMA and FDMA have exactly the same spectral efficiency, but practically, each has its own challenges: power control in the case of Cdma, timing in the case of TDMA, and frequency generation filtering in the case of FDMA. TDMA systems must carefully synchronize the transmission times of all the users to ensure that they are received in the correct time slot and do not cause interference. Since this cannot be perfectly controlled in a mobile environment, each time slot must have a guard time, which reduces the probability that users will interfere, but decreases the spectral efficiency. Similarly, FDMA systems must use a guard band between adjacent channels, due to the unpredictable Doppler shift of the signal spectrum because of user mobility. The guard bands will reduce the probability that adjacent channels will interfere, but decrease the utilization of the spectrum. Flexible allocation of resources. Asynchronous Cdma offers a key advantage in the flexible allocation of resources, that is, allocation of APN codes to active users. In the case of CDM, TDMA, and FDMA, the number of simultaneous orthogonal codes, time slots and frequency slots respectively are fixed, hence the capacity in terms of number of simultaneous users is limited. There are a fixed number of orthogonal codes, time slots or frequency bands that can be allocated for CDM, TDMA, and FDMA systems, which remain underutilized due to the bursty nature of telephony and packetized data transmissions. There is no strict limit to the number of users that can be supported in an asynchronous CDMA system, only a practical limit governed by the desired bit error probability, since the SIR varies inversely with the number of users. In a bursty traffic environment like mobile telephony, the advantage afforded by asynchronous CDMA is that the performance is allowed to fluctuate randomly, with an average value determined by the number of users times the percentage of utilization. Suppose there are 2 end users that only talk half of the time, then 2 end users can be accommodated with the same average bit error probability as end users that talk all of the time. The key difference here is that the bit error probability for end users talking all of the time is constant, whereas it is a random quantity for 2 end users talking half of the time. In other words, asynchronous CDMA is ideally suited to a mobile network where large numbers of transmitters each generate a relatively small amount of traffic at irregular intervals. CDM, TDMA, and FDMA systems cannot recover the underutilized resources inherent to bursty traffic due to the fixed number of orthogonal codes, time slots or frequency channels that can be assigned to individual transmitters. For instance, if there are n time slots in a TDMA system and 2 n users that talk half of the time, then half of the time there will be more than n users needing to use more than n time slots. Furthermore, it would require significant overhead to continually allocate and deallocate the orthogonal code, time slot or frequency channel resources. By comparison, asynchronous CDMA transmitters simply send when they have something to say, and go off the air when they don't, keeping the same PN signature sequence as long as they are connected to the system. Spread spectrum characteristics of CDMA. Most modulation schemes try to minimize the bandwidth of this signal since bandwidth is a limited resource. However, spread spectrum techniques use a transmission bandwidth that is several orders of magnitude greater than the minimum required signal bandwidth. One of the initial reasons for doing this was military applications including guidance and communication systems. These systems were designed using spread spectrum because of his security and resistance to jamming. Asynchronous CDMA has some level of privacy built in because the signal is spread using a pseudo-random code. This code makes the spread spectrum signals appear random or have noise-like properties. A receiver cannot demodulate this transmission without knowledge of the pseudo-random sequence used to encode the data. CDMA is also resistant to jamming. A jamming signal only has a finite amount of power available to jam the signal. The jammer can either spread its energy over the entire bandwidth of the signal or jam only part of the entire signal. CDMA can also effectively reject narrowband interference. Since narrowband interference affects only a small portion of the spread spectrum signal, it can easily be removed through notch filtering without much loss of information. Convolution encoding and interleaving can be used to assist in recovering this lost data. CDMA signals are also resistant to multipath fading. Since the spread spectrum signal occupies a large bandwidth, only a small portion of this will undergo fading due to multipath at any given time. Like the narrowband interference, this will result in only a small loss of data and can be overcome. Another reason CDMA is resistant to multipath interference is because the delayed versions of the transmitted pseudo-random codes will have poor correlation with the original pseudo-random code, and will thus appear as another user, which is ignored at the receiver. In other words, as long as the multipath channel induces at least one chip of delay, the multipath signals will arrive at the receiver such that they are shifted in time by at least one chip from the intended signal. The correlation properties of the pseudo-random codes are such that this slight delay causes the multipath to appear uncorrelated with the intended signal, and it is thus ignored. Some CDMA devices use a Rake Receiver, which exploits multipath delay components to improve the performance of the system. A Rake Receiver combines the information from several correlators, each one tuned to a different path delay, producing a stronger version of the signal than a simple receiver with a single correlation tuned to the path delay of the strongest signal. Frequency reuse is the ability to reuse the same radio channel frequency at other cell sites within a cellular system. In the FDMA and TDMA systems, frequency planning is an important consideration. The frequencies used in different cells must be planned carefully to ensure signals from different cells do not interfere with each other. In a CDMA system, the same frequency can be used in every cell, because channelization is done using the pseudo-random codes. Reusing the same frequency in every cell eliminates the need for frequency planning in a CDMA system. However, planning of the different pseudo-random sequences must be done to ensure that the received signal from one cell does not correlate with the signal from a nearby cell. Since adjacent cells use the same frequencies, CDMA systems have the ability to perform soft handoffs. Soft handoffs allow the mobile telephone to communicate simultaneously with two or more cells. The best signal quality is selected until the handoff is complete. This is different from hard handoffs utilized in other cellular systems. In a hard handoff situation, as the mobile telephone approaches a handoff, signal strength may vary abruptly. In contrast, CDMA systems use the soft handoff, which is undetectable and provides a more reliable and higher quality signal. Collaborative CDMA. In a recent study, a novel collaborative multi-user transmission and detection scheme called Collaborative Cdma has been investigated for the upper-link that exploits the differences between USERSA unregistered trademark fading channel signatures to increase the user capacity well beyond the spreading length in multiple access interference limited environment. The authors show that it is possible to achieve this increase at a low complexity and high bit error rate performance in IAT fading channels, which is a major research challenge for overloaded CDMA systems. In this approach, instead of using one sequence per user as in conventional CDMA, the authors group a small number of users to share the same spreading sequence and enable group spreading and despreading operations. The new collaborative multi-user receiver consists of two stages: group multi-user detection stage to suppress the MAI between the groups and a low-complexity maximum likelihood detection stage to recover jointly the co-spread USERSA unregistered trademark data using minimum Euclidean distance measure and USERSA unregistered trademark channel gain coefficients. In CDM, signal security is high. See also. Further reading: Viterbi, Andrew J. CDMA, Principles of Spread Spectrum Communication. Prentice Hall Ptr. ISBN A0-201-63374-4, CDMA Spectrum. Retrieved April 29, 2008. References. External links: CDMA Development Group, talk at Princeton Institute for Advanced Study on Solomon Golong's work on pseudorandom sequences.